Hello there and welcome back to this video series on control systems. In the last video, we have seen what we mean by a signal flow graph, how to draw a signal flow graph, and we have introduced terms such as a loop, a forward path, and touching loop or forward path, that is two touching loops or one loop touching a forward path. We will try to use these and try to specify what is Mason's gain formula and go over an example. After watching this video, perhaps you will be able to draw a signal flow graph to represent a set of equations and then apply Mason's gain formula to find the gain between an input node and an output node. I would strongly urge you to watch this video 026, which is a preliminary video, before going through this video. That way you'll make the most out of it. This formula, which perhaps was invented by Samuel Jefferson Mason, allows us to find the gain between an input node and an output node, which is precisely the transfer function in a single step, in one stroke, rather than having several simplification steps as done in the case of log diagram reduction. Okay, this Mason's gain formula specifies the gain from an input node to the output node, and in doing that it will use terms involving forward paths and loops. That is why it is very good if you are familiar with what we mean by forward path and a loop. The beauty is all these kind of computation or the simplification involved is done visually. There are perhaps 4 steps in evaluating gain using Mason's gain formula. One is finding the loops and computing what is called a determinant of the graph, then identifying forward paths, identifying cofactors from the determinant, and then using the formula. Remember, loops and determinant, forward paths, cofactors, and Mason's gain formula. So we try to define what we mean by gain of what we mean by determinant of a signal flow graph. Though it appears kind of formidable, the determinant is very simple. It is 1 minus sum of all the loops, sum of products of non-touching loop combinations, sum of products of 3 non-touching loop combinations, and so on. This will become clear if you work through a couple of problems. Just remember, this determinant is 1 minus sum of all loops plus sum of product combinations of 2 non-touching loops. Here it is 3 non-touching loops, and so on. 1 minus plus minus plus, and so on. It will alternate. If you remember this, you can very easily compute the determinant. We have already defined a forward path is a path going from an input node to an output node without touching any node more than once. That is, forward path is simply the number of ways in which you can start at an input node and reach an output node without touching any other in-between node more than once. And while you are going along this forward path, you take gain along each segment and multiply that. The final product is called gain of the forward path. Gain of the forward path we represent by P. If it is ith forward path, the gain is Pi. Let us say there are n forward paths, capital N forward paths. There will be as many cofactors as there are forward paths. So if n is the number of forward paths, you have n is the number of cofactors. The kth cofactor, delta k, is found by removing from delta all the loops touching the kth forward path. So if you are forward path 1, okay, you remove all the loops touching first forward path, what is remaining is delta 1. If you remove from delta all the loops that are touching second forward path, it is delta 2, and so on. Once you identify the number of loops and number of non-touching loops, combinations of two non-touching loops, and so on, delta is found. Okay, and once you identify the forward paths and their gains, pk is found. Remove from delta the paths touching first forward path, second forward path, and so on. You can find delta 1, delta 2, delta 3, and so on. You can plug it in here to find the gain from the output node to the input node. So once the loops and forward paths are identified systematically and noted down, transfer function or gain from any input node to any output node may be found in one stroke. We will try to illustrate this with an example. The example may be slightly, it may appear slightly complicated to begin with, but if you realize this is the same example as we have done in the previous video, so go back, watch it, and then come back. It will be very clear to you. So we say that we have this set of equations, and then we drew a signal flow graph here, and now we start applying Mason's gain formula. For finding the determinant, that is the first step in applying Mason's gain formula MGF, you need to identify loops. We have counted that there are 8 loops in the signal flow graph. So we apply the formula to find delta 1 minus sum of all the loop gains. L1 and L8, L4 and L6 we have taken because only these are non-touching. L1 and L8 do not have any common node. L4 and L6 do not have any common node. That is why you have included them. If there is something common, even this L1, L8, L4, L6 will also not come. So this is the determinant. And then you identify forward paths. As we have noted, there are 3 forward paths, P1, P2, P3. Corresponding to each one of these, you have delta 1, delta 2, delta 3. So in delta 1, you remove all the terms, okay, all the terms that have something in common with path 1. Okay, for path 1, if you remove all the touching loops, only 6 is remaining. L6 is remaining. So delta 1 is 1 minus L6. You can carefully notice R, X1, Y1, C, that is path 1. And see this loop 6, X2, X3, X2. Okay, this path X2, X3, X2 does not have any node common with path 1. So delta 1 is 1 minus L6. Similarly, if you see node 2 touches each and every loop. So you have to remove all the loops, you are left with 1. That exactly see what we have done. We have found from path 1, okay, which loops are touching path 1. Okay, if a loop touches, you remove it. So you removed all the things and you retained 6. That is why you have 1 minus L6. Similarly, delta 2 is 1, delta 3 is 1. So you know what is P1, P2, P3, delta 1, delta 2, delta 3, and thus you find the overall gain from output to the input, that is C by R, is P1 delta 1 plus B2 delta 2 plus P3 delta 3 by delta. See, you can in one stroke you found the transfer function. I would strongly urge you to go back, do this problem on your own and compare your result with this. I think that's all we have. To summarize, Mason's gain formula is seen as an elegant, algebraic, combinatorial and visual tool, and we presented one example. We'll see two or three more examples and conclude this topic. That's all for now. Have a great day.